So, in the previous discussion we had the equation which was of the form x dot equal to Ax. Now, this is a linear equation, so it has eigenvalues and eigenvectors. So, for our case the equation was 2D, right, x u2 and theta. So, it has 2 eigenvalues and 2 or less eigenvectors, but I will show you that there are 2 eigenvectors. Okay. Now, the eigenvalues will tell us whether system will grow or not, I mean the velocity field will grow or not. And how does eigenvalue tell you? So, we look at the general solution. So, look, so these are the 2 eigenvectors, okay, these are 2 eigenvectors. Now, if my initial condition is along this eigenvector, then depending on the eigenvalue it will either increase in length or decrease in length. Same thing for if my initial condition is along V2, it will decrease or increase. Lambda being negative is decay, lambda being positive is growth, lambda being complex could have oscillations. Okay. Now, if it is combination of the two, so my initial condition let us say somewhere here, then it will not grow along that line, it can go in some different direction depending on how much contribution it gets from V1 and V2. Okay. So, the general solution is this. From the initial condition you can get CIs, and once you have the CIs, then we can get this x as a function of time. Okay. So, this is how we solve in linear algebra. Okay. So, our objective is to find the eigenvalues and also eigenvectors. So, eigenvectors will tell you how the flow profile will look like. I am going to tell you how. Okay. So, this part I will tell you how. So, let us look at our equation. So, this is the equation which I had written. Okay. Now, please remember the sine zeta, right, zeta is equal to what, k per by k. Why? Because this is my angle zeta and this k per and this k. So, this z axis and this x axis. I made slight, okay. So, this is what I had. Okay. So, this is what I am doing. Now, so what we should look for is eigenvalues of this. So, for 2 by 2 matrix is a simple formula for eigenvalues, which is this. Okay. Now, this I memorize it, half trace plus minus trace squared minus 4 determinant. Okay. Now, trace is, you know, the sum of the diagonal elements. So, PR, so this one is minus PR k squared minus k squared, this trace. What is delta trace determinant is PR k4 multiply this with this minus this with that. So, RA PR k per squared by k squared. Okay. Now, let us look at whether, so can you say that one of the eigenvalues is always negative? Because trace is, if you must know this theorem, lambda 1 plus lambda 2 equal to trace, sum of the eigenvalues equal to trace, that is a theorem of linear algebra, and the product of eigenvalues is the determinant. Okay. Now, let us look at first. So, if the sum is negative, and of course, we need to check whether they are real or not. If they are complex, then here it has to be complex conjugate of each other. In the imaginary part must cancel, because this is real, Prandtl number is real, okay, k squared is real. Okay. So, let us first see whether the eigenvalues are real, and how do I know it is real? If this is real, I need to check these quantity. If trace square minus 4 delta 4 determinant is positive, then I know that my eigenvalues will be real. Okay. So, this is bit of algebra, but you can easily do it. Trace squared minus 4 determinant, this is equal to that and is always positive. Okay. This algebra I will not do it right now, but you can easily show this. So, if this is greater than 0, then my eigenvalues are always real. Now, if it is real, then and the sum is negative, that means at least one of them must be negative. Okay. Now, so what happens really? So, we can just check. Now, if they are negative, both of them are negative, let us say. So, what happens to the determinant? Positive. If one of them becomes negative, then one of them negative, other one becomes positive, then determinant becomes negative. So, it changes from positive to negative and it goes through 0. So, we look for the transition. So, when will the transition take place? When determinant is 0. Okay. Now, do you recall the formula for Rayleigh number? Rayleigh number is alpha g delta d cube by nu kappa. Okay. If so, you can see that this is positive PRK4. Now, this Rayleigh, if it is 0, then determinant is positive, right. So, if the temperature difference is 0, then determinant is positive, that means both the eigenvalues will be negative, because you see the determinant can become positive if both of them are same sign, and one of them is definitely negative, the other one must be negative. You keep increasing Rayleigh, at some point the determinant will become 0, because Rayleigh is the only parameter which I am tweaking. My tweak parameter is Rayleigh, and when Rayleigh crosses some critical value, then it becomes determinant becomes negative. That means one of the eigenvalue has become positive, and eigenvalue becoming positive is what? Growth. I mean, it's quite clear the eigenvalue positive is growth. So, we look, so lambda equal to 0 is a transition when determinant is 0, and that is called neutral stability. So, neutral stability, and at this situation, in this situation, my say the u2 and theta will not grow, they will just stay there, but immediately after Rayleigh, beyond Rayleigh critical, the growth will start. So, the condition I know now is easy. When increase Rayleigh, it becomes positive to negative, that is correct. So, the transition happens when determinant is 0, and now you can easily see what is the value of Rayleigh. Rayleigh PR cancels. So, it is k to the power 6 divided by k power squared. So, what is wave k is a wave number and k perp is component of the wave number. So, given wave number, I know what should be Rayleigh critical actually. Rayleigh. So, I define by Rayleigh critical RAC. Now, how do I? So, k is related with the box roll size. Now, if you recall what was my definition of the Fourier modes, so I am going to write it here. I will not go back to those definitions. So, u2 was, or theta, let us look at theta. Theta was sin n pi z exponential I k perp dot r perp, correct, that is what I made, right. So, along, so theta, so I know how, so basically at the vertical direction my roll will be like that, okay. In fact, we know from our school days like this, and horizontal direction it is periodic. So, in fact, I need to worry about the size of a pair of roll like this. So, my box size will determine k perp. So, I am going to come to that, okay. I am going to show you a bit of it, but you can easily see that the dimension of the roll will tell you k perp and k. Well, k parallel is n pi, no, that is kz, and k perp is in the horizontal direction wave number, is coming from kx. One more point, let us just make sure you understand this one, that my u1 is 0, that means it is a 2D system. So, I am going to choose my 2D system, that means my velocity field is u2 and I am going to choose xz, x and z. So, I say my velocity field lies in xz plane, okay, and so my k perp is nothing but kx, k perp is kx, this k perp, and this is k parallel which is kz, and which is always n pi, here kz is n pi. Everybody is happy with me? Okay, now let us do some more analysis. So, but this is where I really have almost derived my condition. I am almost done, not fully, that I have this Rayleigh number at which the instability will start. Now, you can easily see that there are many possibilities of k, right, because there are many n's are possible, many k's are possible. So, we need to see which one among them grows fastest or grows first. So, this is my Rayleigh critical. So, given n k per, I have this formula. Now, I am looking for which value of, let us say I fix n, which value of k per Rayleigh critical will be lowest. No, as I said, no, the most noisiest student is the person, you can make that person. So, if some chance that noisy student will start making noise. So, we are looking for the most unstable system. I do not mean to say noisy student is unstable, but I am just trying to make an analogy. Okay. So, the most unstable mode. So, we keep our k general, but now we are looking for which among them will get unstable earliest. So, I plot this Ra critical. So, now for n equal to 1, the red curve. So, you see so I have plotted for different n's. So, this is n equal to 1, n equal to 2, n equal to 3. You can easily see from here that if I keep k per fixed and increase n, then n equal to 2 has larger than n equal to 1, obvious. Okay. But for given n, so you see right now if I keep more n, then it will be even bigger. So, this y axis is Ra critical and this k per. Now, given n, there is a minima at some k per. So, right, n equal to 1 for some k per, in fact this value is a minimum. So, that will tell me which k per will get excited first. So, how do I find this? It is easy. So, I fix n and I do this. In fact, since n is fixed, I can do the total derivative, this is equal to 0. Now, this only set of algebra, this gives you condition that k per is n pi by root 2. In fact, from the figure you can see this pi by root 2, 2 pi by root 2, 3 pi by root 2, these are minimum. So, n equal to 2 is here, n equal to 3 is here, but the figure does not prove it, but you can easily show from this derivation. Okay. So, now once I put this k per, then I can get Ra critical for given n. Formula is 27 pi 4 by 4 n squared, I believe. Okay. So, that is the Rayleigh critical for any n. Is that correct? Anyone remembers it from the book? I derived this for given n, but it should be, well, indeed, so it should be n cube or n 6, right? Rayleigh critical n squared, it's n squared here, pi 4. Okay. So, there is a actually for n equal to 1, I definitely know it's 27 pi 4 by 4. You can, let's plug it in. So, I put here, then I get n square pi square. So, that becomes n to power 6 divided by n. So, this should be n 4, right, because n 4, it should be n 4. Okay. So, there is a typo in the book actually. Yeah. So, n 4. Okay. So, this is my Rayleigh critical. So, n equal to 1, it is 27 pi 4 by 4, which is 657.511, like that. Okay. So, for this Rayleigh critical, my system will become n equal to 1 mode will, so for this number n equal to 1 will become unstable. For this k per, okay. Now, this k per also tells you the size of the roll, the convection roll, which you studied in your well, it is there in now middle school textbooks. So, k per is n pi by root 2, n equal to 1. So, what should be my wavelength? Wavelength is 2 pi by k per, right. The wavelength is x axis, remember is e to the power I k perp r perp, which is e to the power I k x x. So, wavelength will be that 2 pi by pi by root 2, which is 2 root 2. So, my horizontal dimension is 2 root 2 and the vertical dimension is n equal to 1. So, in vertical direction I have sin pi z. So, remember I told it is a non-dimensional box. So, z equal to 0 and z equal to 1. So, vertical dimension is 1. So, my box is basically like this. So, this dimension is 1 and this is 2 root 2 and my rolls will be is a pair. So, I have better picture in the next slide, but it goes like this and it is a periodic. So, same thing reappear after this. If I choose my origin somewhere here, then I will get half the roll here and other half will come. So, remember, so this half, if I remove this half, so it is a possibility that we may get something like this, like this. So, this has to complete. So, what will I get here? This is coming up like that. So, this roll is periodic boundary condition. So, you please remember that this guy has to be replicated. This box comes here and it will come here. Okay, is that clear? So, pair of roll will be contained in dimension 2 root 2 along horizontal. So, this is what I had said, this is a typo, this should be N4. Okay, so there is N square, I missed N4. Okay, so this is generated from the computer. So, 2 root 2 is around 3. Okay, so 1.2 2.8 2.8. So, this is 2 root 2 and the 2 rolls, you can see the arrows are going like this, arrows are going like this, and so my origin is where the arrow is starting to go up. Okay. Of course, it could be shifted and vertical dimension is 1. So, in summary, so let us summarize. So, how did I start? I started with equation for the velocity field and temperature field, remove the nonlinear term, then we linearized equation, go to Kreyszig-Hairy basis, then I get 2 linear equations, u1 becomes 0, u2 is remains well, u2 could be non-zero, and these 2 equations I find the eigenvalues and eigenvectors. Well, I have not yet found the eigenvector, so I need one slide. Okay, so we got the velocity profile, but actually I just constructed from so this was the basis function, I just plotted it, but I want to know exactly what are the base eigen directions, what is the relationship between theta and u. Okay. So, this was velocity amplitude is fine and velocity amplitude will grow in time. So, I want to derive that stuff. Okay. So, just pay attention to this part. So, we look at my equations were u2 dot theta dot equal to, I am going to write minus PR k squared RA PR k per by k squared, no square, k minus k squared u2 theta. So, how do I find the eigenvector? So, there are 2 eigenvalues. So, what are the 2 eigenvalues? For neutral stability, let us look at for neutral stability. So, neutral stability has one of the eigenvalue is 0. So, I will call it lambda plus, other one is always negative, lambda minus is. So, the sum is already known as PR plus 1 k squared. So, that must be lambda minus because sum must be PR plus 1 k squared. So, I can find the eigenvectors for these. It is easy, no? This equal to, in fact, for 0 eigenvalue I erase this one, this must be 0 for 0 eigenvalue. Okay. So, that gives you eigenvectors. So, let us work out for the eigenvector k perp by k. So, I am going to call this is u2 minus k squared theta is 0. So, that gives me, I am going to make theta as 1. Okay. So, that gives me u2 which is k cube by k perp. So, my eigenvector is minus k cube by k perp in 1. So, this corresponds to lambda equal to 0. So, other one, how do I find the other one? So, instead of 0 I put minus PR plus 1 k squared times this vector, correct. So, that gives me, I will not do the algebra which is straightforward. So, lambda equal to minus PR plus 1 k squared. So, by the way, the two equations are not independent, no? They are exactly same here. One of them is enough because the length of the eigenvector is not unique, any length is fine. So, that gives you b is equal to 1. I can choose, I can multiply this by any number, still this eigenvector, and that is PR k cube by k perp. What is k cube by k perp? Now, we just had the formula. So, k6 by k perp square was Rayleigh critical, right. So, this is nothing but square root Rayleigh critical. Why do I need to write all this? So, I just put Rayleigh minus Rayleigh critical. Okay. So, minus Rayleigh critical. So, now we can plot them. Now, by the way, now this is the answer. So, my temperature and velocity field are related. If the temperature amplitude is 1, then my velocity amplitude will be what? Will be this or that? Which one of the two? Huh? First one. Why first one? So, my the solution is, if you recall, it was Ci, then Vi eigen direction exponential, this is a vector, exponential minus lambda t, lambda I t. So, this eigenvector in that direction, my amplitude will go to 0 because my lambda is negative. So, I have this vector. So, if I choose any arbitrary direction, so let us first plot the eigen direction. Okay. So, please keep in mind that this will go to 0. So, I am going to change my color. So, let us plot them. Okay. So, this is my u2 direction and the theta direction. Theta is y axis, theta is y axis and u2 is x axis plus lambda, you are right, thank you, sorry, thanks. Yeah. So, what is the first one? So, y axis is 1, right, I am choosing y theta to be 1, right, the theta is 1 for both of them. First one is minus Rayleigh critical square root. So, this is minus Rayleigh critical. So, this is minus square root Rayleigh critical. This guy is x component is proportional to Prandtl. So, Prandtl bigger than 1 it will go in that direction, Prandtl less than 1 it will go here, Prandtl equal to 0 it will be here. Okay. So, this is the first eigenvector which V0 I can call it V0. This is not velocity field, this is eigenvector, and the other eigenvector depends on Prandtl number, it is somewhere here, depends on the Prandtl number. Now, if my u2 theta, they are real numbers, well I choose amplitude is real here. Now, only this component will survive, this component along this direction will decrease to 0. So, if I choose any initial condition here, this algebra, linear algebra, I do not need to emphasize it. You take a component of this along this direction, how do I take the this direction and this direction? They are all non-orthogonal, no? Like this. So, this component will go to 0, this component will, in fact, it does not increase, it will remain. So, this will remain like that. Is that clear? So, I know what is the steady state for this Rayleigh critical. or Rayleigh number, Rayleigh critical. It should be just this. Okay. So, I plotted only the velocity field. From U2 you can compute Ux and Uz, right, by the formula which I gave you, and once you know Ux and Uz, you can plot the figure I showed you, and once you have the Ux and Uz, you can also compute temperature precisely, because the neutral stability gives you that the velocity field and temperature field are related. Okay. So, this is how we compute it, both. Now, what happens when I increase my Rayleigh number a bit more? So, my eigenvector will change or eigenvector will remain same, because my matter, so my eigenvalue will become positive, right. So, my eigenvalue becomes positive, so my eigenvector will change, it will not remain exactly same eigenvector, but near the onset it will be approximately in that direction, approximately. Okay. So, near the onset means my Rayleigh number is 1.1 Rayleigh critical, then still my rolls will be behaving something like original roll, but if you make it too large, then of course things will not work. Okay. So, we can analyze all this using this linear stability analysis. So, eigenvectors will give you very useful information, and I am going to show you in the next example that it will be more interesting. So, any question on this? Okay. So, after instability, so basically the eigenvector and eigenvalue tells you about the roll structure near the onset, okay, both temperature and velocity field. Now, since my eigenvalues are positive or real, actually real, okay, and it changes from negative to positive, so it will be basically 0 before and becomes only growing rolls, it will not be oscillating rolls. So, these are called stationary. So, what we get for Rayleigh-Benard is stationary. So, it will grow, but it is not oscillating, okay. So, non oscillating, but sometimes, okay, you can get complex, eigenvalue becomes complex. My eigenvalue is real right now, but it could become complex, then the imaginary part will give you oscillations. So, first thing I know is that it is going to be a stationary roll, stationary not in the sense of time independent, the amplitude will keep growing, okay, but no oscillations. So, what does it mean by amplitude growing? So, if you recall, my theta was theta of k t I did not write sometimes, but sin pi z for primary mode e to the power I k x x. So, this is growing, that means our velocity field is u vector k t, and of course, depends on sine and cosine and so on. Now, what does it mean? That my velocity field any position will be keep. So, if my amplitude is changing, then it is going faster and faster, is going faster and faster. Now, so that is what is instability. So, this will keep growing faster and faster, but will it saturate at some point? So, can any real system just things can keep growing? So, somewhere it should saturate or something should stop growing, and what will make it stop to grow? Molecule. So, by the molecular diffusion is included in my derivation. So, viscosity is included in this. Viscosity cannot. It is a nonlinear saturation. Please keep in mind that if you had viscosity equal to 0 and diffusivity is 0, then any temperature will make it grow. You have to wait till Rayleigh critical because of viscosity. You can look at the equation. If you turn off the nu and kappa, it is unstable at the onset itself. Well, now that means any temperature if you give, it will just grow. So, Rayleigh critical is Rayleigh critical, non-zero Rayleigh critical because of viscosity and diffusivity. So, you need nonlinear saturation, nonlinear term to kick in for growth to stop. Okay. So, we will do that bit later, not today, but we will do it tomorrow possibly. Now, this was a finite Prandtl number, what I showed you is a finite Prandtl number, but we can do interesting cases, interesting study of the extreme cases, PR 0 and PR infinity, okay, or PR small. But please keep in mind that my Rayleigh number was independent of Prandtl number, Prandtl got cancelled. So, my Rayleigh critical does not depend on the Prandtl number. Only thing it depends is, well, I will not answer this question, but I would want you to think about what happens for Prandtl number 0. Okay, this is an interesting case, Prandtl number 0. Rest all is basically not so complicated, but that is an interesting case. Okay, so I will stop here. So I hope I answered the questions which was asked. Thank you.